created by MindSticks Foundation Trust.
Hello students, and welcome to today's Explainer. Today's agenda is structured into 4 clear parts. First, beyond the right angle. Second, the Apollonius theorem. Third, solving geometric examples. And finally, test your understanding. Let us begin.
Section 1. Beyond the right angle, acute and obtuse triangles.
We are all very familiar with the standard Pythagoras theorem, right? It is the backbone of geometry for perfect 90-degree angles. But what happens when that angle shrinks? Let us look closely at this figure. Observe triangle ABC. Here, angle C is strictly an acute angle, meaning it is less than 90 degrees. To understand the relationship of the sides here, we draw a perpendicular segment, an altitude AD, straight down to the base BC. This simple construction neatly divides our original shape into 2 separate right-angled triangles, triangle ADB and triangle ADC. By applying our basic Pythagoras theorem to these 2 smaller triangles, we can find a mathematical relationship for the side opposite to our acute angle.
And this brilliantly illustrates the resulting relationship. The formula for the side opposite the acute angle is AB squared equals BC squared plus AC squared minus 2 times BC multiplied by DC. Now, the crucial point is that it looks very much like the original Pythagoras theorem, doesn't it? But because the angle is closed in and is less than 90 degrees, we must subtract that extra rectangular area at the end, the minus 2 BC into DC. This adjustment perfectly balances our equation.
Now, let us see how this builds when the angle changes. Direct your attention to the next figure. Notice how angle ACB has now opened up wide. It is an obtuse angle, so it is greater than 90 degrees. Because of this wide angle, when we drop our altitude AD, it actually falls entirely outside the main triangle. We have to extend the baseline from C to D just to meet it. But the logic we apply remains exactly the same. We once again use Pythagoras on the large right-angled triangle ADB and the smaller one ADC.
When we substitute the values, we arrive at the obtuse angle formula. AB squared equals BC squared plus AC squared plus 2 times BC multiplied by CD. Do you see what happened here? Because the angle has opened up and become obtuse, the side opposite to it, AB, has naturally become longer. Therefore, to make the equation balance, we must now add that extra rectangular area. That plus sign is the absolute key difference here.
Let us pause and compare the 2 formulas side by side to really solidify this in our minds. For the acute triangle, we have a minus sign at the end, minus 2 BC into CD. For the obtuse triangle, we have a plus sign, plus 2 BC into CD. It is a simple, elegant symmetry. If the angle is smaller than 90, we subtract. If the angle is larger than 90, we add. Understanding this basic difference is exactly what will help you master the next very important topic.
Section 2. The Apollonius theorem, a magical shortcut.
We are going to take the 2 formulas we just learned and combine them into a truly magical shortcut. But before I show you the formula, think about this carefully. What happens if we draw a median instead of just an altitude? Remember, an altitude simply drops straight down at 90 degrees, but a median goes directly from the vertex and hits the exact midpoint of the opposite side, cutting the base into 2 perfectly equal halves. How does that midpoint change our geometry? Take a look at this next figure. Here, segment AM is not just an altitude, it is a median. Point M is the exact midpoint of side BC. Because AM is a slanted median, it creates 2 different angles at the base. Observe how angle AMB on the left is clearly an obtuse angle, while angle AMC on the right is an acute angle. This means one half of our triangle follows the obtuse formula we just learned, and the other half follows the acute formula. When we write down both equations and simply add them together, something beautiful happens. That extra rectangular area, the plus 2 BC into CD and the minus 2 BC into DC, they are completely equal because M is the midpoint, so they cancel each other out entirely. This leaves us with a clean, elegant Apollonius theorem. AB squared plus AC squared equals 2 times AM squared plus 2 times BM squared. In simple terms, the sum of the squares of the 2 sides equals twice the square of the median plus twice the square of half the base. It is a brilliant shortcut linking the sides directly to the median.
Section 3. Solving geometric examples, putting theory into practice.
Now that we have this powerful theorem in our toolkit, let us see exactly how much time and effort it saves us on typical exam problems. Let us closely examine this classic problem. We are given triangle PQR. We know that PM is a median, which immediately tells us M is the midpoint of QR. The problem gives us the length of the median PM as 9. It also gives us the sum of the squares of the two sides. PQ squared plus PR squared equals 290. Our task is to find the total length of the base, QR. Without Apollonius, this would take pages of calculations. Let us see how quickly we can solve it now. We simply follow the logical steps. Step 1, we identify the median PM, so we know Apollonius applies. Step 2, write the formula. PQ squared plus PR squared equals 2 times PM squared plus 2 times QM squared. Step 3, we substitute our known values. The left side is completely given as 290, so 290 equals 2 into 9 squared plus 2 into QM squared. 9 squared is 81. 2 times 81 is 162. We bring 162 to the other side. 290 minus 162 gives us 128. Divide by 2, and we get QM squared equals 64. Taking the square root, QM equals 8. Finally, step 4, since QM is only half the base, we double it. 2 multiplied by 8 gives us our final answer, QR equals 16. A complex problem solved in just 4 easy steps.
Let us move to another beautiful application. Take a look at this shape. The Apollonius theorem is not just for finding numerical lengths, it is also a fantastic tool for proving properties of shapes. Here we have a rhombus, PQRS. The diagonals PR and SQ intersect at point T. We need to prove that the sum of the squares of all 4 sides is equal to the sum of the squares of its 2 diagonals.
We can break this proof down into very clear, digestible points. First, we use the fundamental property that the diagonals of a rhombus bisect each other. This means point T is the exact midpoint. Therefore, PT acts as a median for triangle PQS, and RT acts as a median for triangle RQS. Second, we simply apply the Apollonius theorem to these adjacent triangles. Third, we take those 2 resulting equations and add them straight down. Because all sides of a rhombus are equal, terms combine perfectly, and the result elegantly falls out. The sum of the squares of the sides exactly equals the sum of the squares of the diagonals. This perfectly demonstrates the immense power of our new mathematical tool.
Section 4. Test your understanding.
You have done incredibly well following along with the theory and the proofs. Now, true understanding comes only when you apply the concepts yourself. Let me direct your attention to a question straight from your practice set. We are given triangle ABC, and we are told that point M is the midpoint of side BC. We are given the length of the median. AM is equal to 8 centimeters. We are also given the combined square of the sides. AB squared plus AC squared equals 290 square centimeters. Your goal is to find the full length of the base side, BC.
So here is my thought-provoking challenge to you. Can you apply the Apollonius theorem to find the correct length of side BC? Think about the steps we took just a few minutes ago. You have the median, you have the sum of the squares of the sides. Set up your equation, substitute the values carefully, solve for half the base first, and remember to double it at the very end. Keep practicing your substitutions, trust in the logic of the theorem, and you will find the correct answer with ease. Thank you so much for joining me in this explainer today. Keep learning, keep practicing, and I will see you in our next lesson.